is related to filtering. So several years ago, I put a new HVAC system in my house, and it has filters on it. And each filter removes 60% of fine particles in the air. And it had a definition of what fine particles meant. I'm not going to worry about that for the moment, but and I can put multiple filters in, right? So one filter removes 60%, two filters removes another 60%. Now, my machine holds 6 filters, and each of them removes 60%, and they run one after the other. Now, we can't add the 60% together because that would remove 120% if I added 2 of them. And there's only 100% of stuff in the air. You can't take more than 100%. That's everything that's there. So the way this works is a couple of things to think about. One, this removes 60%. So if you think about it as a rate, R, 60% as a decimal would be 0.6. And it is a negative rate because I'm removing stuff. We've had our formulas where we did 1 minus R. So if I take 1 minus that 60%, that leaves me with 40% remaining. So the first filter works and it leaves 40%. Then the second filter acts on that. So 100% of the particulates come in. The first filter takes out 40% of them. The second filter takes 40% of that, and these just keep applied like compound interest or a car balance, a car depreciating over time. And so for every one of my filters, I get to multiply. It's going to take out 40% of whatever was left. And I'm just going to keep doing that for all 6 filters. So there's 1, 2, 3, 4, 5, 6. Now, we learned earlier a better way to write repeated multiplication is exponents. So this would be 1 times 0.4 to the power 6. So if I can see what happens if all 6 filters are working properly, oops, calculator please. What is 0.4 raised to the 6th power? There's only 0.4% of the particulates that are left behind. So 0.004. So that is approximately, come on pen, just different color, 0.004. As a percentage, that would be 0.4% of the particles are left behind. Okay, so it took out quite a bit. Maybe I want it to be even less than that, or maybe it doesn't need to be that fine. So we're just going to play a little game here. How many filters are needed to leave about 2% of the fine particles behind? So to answer this question here, I need to change that situation into an equation. And let's say we're just going to use y for the amount of particles. And x is the number of filters I need. So the formula is going to look something like y equals p times 1 minus r to the power x. Since I'm talking about percentages here, my P gets to be 1. My R was that 60%. 1 times anything outside doesn't do anything, so really all that matters is this base right here, which is the 0.4 I was using on my calculator a minute ago. And for the Y, I want to know when the Y is 2%, so that would be 0.02. So that's putting all the information together. How do we solve an equation where I don't know the exponent? Anyone? How do we solve for an exponent?
Wouldn't we just do the log?
Yeah, logarithm. Anytime it's a missing exponent, we do a logarithm. So new page. So I'm starting with the equation 0.02 equals 0.4 to the power x, and I just rewrite it taking the log of both sides. Once I do that, I can pull the exponent out in front of the log here. So that's going to be x times the log of 0. Oops, I wrote that wrong. It should be 0.4. Make sure you copy things correctly. And the other side, I still have log of 0.02. Now, this is just a number I'm multiplying by x, so I can divide by the whole log. And the log is stuck with that number. They are inseparable. A number divided by itself is 1. 1 times x is x. So now I've solved for x. It's whatever my calculator says that log fraction is. And remember, the logs don't cancel. I'm stuck with them. So for this situation, I would have the log of 0.02 divided by the log of 0.4. And this says I would need 4.269 filters. Now it's either a whole filter or not, right? So if I went 4 filters, that's a little less. 5 filters would be a little more, so we'd have to make a decision there. So let's just check, it's 4 or 5 filters. And the question is, should you always round down? And that depends on what your outcome is. So just double check, if I take the 0.4 raised to the power 4, that gives me about 2.5% left, 0.0256. If I take 0, let's use a different calculator for fun, 0.4 raised to 5 filters instead, then I will have about 1% of the particulate matter left behind. So I get about 4.3-ish here. So the question is the answer 4 filters or 5 filters? Oops, I'm supposed to be an or there. And at 4 filters, that leaves Y at about 2.6% is what I calculated on my calculator, plugging it back into the formula. At 5 filters, Y ends up being 1%. Okay. And so if they said it's got to be at least 2%, then this wouldn't work. I would have to go with 5 filters. So it depends on the outcome. Do we just need to be close to 2%, or does it have to be 2% or less? 2% or less, then I got to jump to 5 filters. I can't do a third of a filter. It's either a whole filter or not. All right, so let me see. One more question, then I'll let you guys work and see if you have any questions for me. So I just did a problem like number 1 from 4.4, which in past quarters people have a hard time with. So in this case, we have polluted water, and each filter removes 90%. That means 10% is remaining. How many filters do we need so we can get from 10 million particles down to 500 particles per gallon? Okay. So I'll come back to that one in a minute after you guys get a chance to try it. I think the hardest question was, let's see, we did a problem like this last week, but that is still a hard one. And then this one is right hard too. So let's take a look at, this one has a pretty thorough written example. Let's go back and do this one right here. So let's look at that caffeine problem again. So we did one of these last class. And it varies just a little bit. I think only on the 6.5 hours. You might have 5.5 or something similar. Copy this. Now, last class, I gave the half-life equation. And it's also in the written example if you get stuck. So the half-life equation looks something like y equals whatever the initial amount is, let's call that p, times parentheses 1/2 raised to the power t over whatever the half-life is. Now in this problem right here, they want me to use a c instead of a y. We're starting with 100 milligrams of coffee, so that's our caffeine, that's our starting. And then we'll have the 1/2 in parentheses, and then the power is going to be, the half-life is given at 6.5 hours. So the power here would be t over 6.5, like that. So the base is 1/2, t over 6.5 is the exponent, 100 is being multiplied outside of that. And the first question just says plug in t equals 10. And that's not too hard. We did one of those last week. The harder question is, when is there 200 milligrams available? So I'm going to go over that part right here. So part C says, when is there 200 milligrams remaining? So they're telling me C equals, sorry, not 200, 20. C equals 20, then we're going to have to plug in and then solve for T. And this is a tough one. So if I plug that in, I'm going to get 20 equals 100 times 1/2 to the power t over 6.5. And when you're solving an equation, you usually get things that are furthest away from the variable out of the way first. So the closest thing to t is the 6.5, next closest is the 1/2, the last thing would be the 100, so that's what I do first when I solve. So I break that multiplication by dividing by 100. Now this cleans up nice. 20 divided by 100 is 2 over 10, which is 0.2. So I'm gonna actually clean that up because it's nice. If that came out to a messy decimal, I would leave it as a fraction. On this side over here, 100 divided by 100 is 1. 1 times this is itself. So on the other side, I now have 1/2 to the power t over 6.5. Since I have the base isolated, I'm ready to use a logarithm. So then I take the log of both sides. And then we have that rule for logarithms that says if you have the log of something to a power, you can pull that power out front as a multiple. So that's what's going to happen next. So log of 2/10 equals, the power was t over 6.5 for mine. And then it's times the log of the base 1/2. Now, keep in mind, the log of 1/2 is just some number. It's being multiplied. So I'm ultimately going to have to divide it to the other side. So I think I'll do that first. And then a number divided by itself is 1. 1 times anything is itself. So on this side, I just have t over 6.5 left behind. And until I get to a calculator, I'm stuck with those logs, but I'm not ready for a calculator. Finally, to get rid of that division there, I can multiply both sides by 6.5. So if I have a number divided by itself, that's a 1. 1 times t is t. And so t must be equal to whatever that is right there. And then it's calculator time. So let's plug it in and check to see if it actually works before we try the submit question. Calculator. So I've got 6.5 times the log of 0.2, close the log parentheses, and then divide by the log of 1/2, 1 divided by 2. Type that right. 6.5 times the log of 2/10 divided by the log of 1/2. Looks right. And my calculator says 15.09-ish. And I want to check to see what that means and if it's true. So if I go back a page, let's see, that was hours. So it looks like 15 hours later, there should be about 20 milligrams. And we can plug back into the original formula here to see if that's true. So I'm going to say it's about 15 for mine. So if I recalculate, let's go over to this calculator, starting with 100 times parentheses 1/2, and then close the parentheses, then go to the power, and I think t is going to be 15, but I have to divide it by 6.5, the half-life. And again, pay attention to what your half-life is. It might not have been 6.5. And this says there's about 20 milligrams left, which is, I was aiming for 20. So that worked out. So remember, practice checking your work on a calculator. Okay, so those are the problems I wanted to go over. Does anybody have any questions that they want to ask about the homework or the lesson? Otherwise, I'm just going to hang out here for the next 10 minutes to see if you want to ask a question. Just feel free to put it in the chat or voice it.
Thank you. Have a nice day.